If life is a matter of knowing, we are on our way to knowing what is matter, basic matter. We think there must be one matter that formed everything, both living and dead. Planets, stars, all that built by the same particles. We think these particles were created at the birth of the universe 15 billion years ago. We can even search back then with the Hubble Space Telescope. Deep in space and far back in time, Hubble's sharp eyes can peek. Look at how it could have been, the very early stages after the Big Bang. The universe, less than 1 billion years old. But let us think back until a split second after the Big Bang. In the first milliseconds, the universe must have been extremely hot and dense, matter in its most basic state, and antimatter. Just after the Big Bang, particles must have been created and destroyed, particles and forces that define the material world of today. Our present knowledge is still limited. More and more questions remain after generations of science. Questions. What exactly happened in those first few seconds? Is there other matter not visible to us? Dark matter. We do our calculations and say particles all have different masses, but we don't know why and how mass was obtained from energy. It seems we have no other choice than to keep on exploring. Here is a tool, the most powerful accelerator ever built, LHC, the Large Hadron Collider. Protons colliding head-on with extremely high energy, the energy of the first split seconds after the Big Bang. Collisions with this energy can show so much. They generate particles that can be seen by detectors like Atlas. Detectors to examine the results produced by the collisions. Atlas. Here's a source of knowledge indispensable for the description of basic matter. But we're bound to meet surprises. We've always tried to understand our universe, pushing our limits. Facing the universe, there came a time when people started to observe and calculate. Ptolemy found the Earth should be the center of everything, the geocentric model. Not until the 16th century did people dare to doubt Nicholas Copernicus, Galileo Galilei. Not the Earth, but the Sun had to be the center of the universe. It was the beginning of an era of experimentation. The fact that matter is attracted by the Earth is described by Newton in equations of great beauty. "300 years later, we are able to control satellites in orbit. Broadcasting, telephones, It is clear how understanding the forces of nature can have an impact on daily life. New physics, chemistry, biochemistry marked the 20th century. The 20th century, remember? Einstein developed his theory of relativity. A new awareness was growing on the constitution of matter. Theories were overhauled for two pivotal elements, mass and energy. Mass and energy are related and can be converted into each other. But why do particles have the masses we observe? Ideas we do have are described in what is called the Standard Model. The Standard Model does answer questions about structure and stability of matter, and about the fundamental forces. The building blocks of matter, the basic particles. Today we recognize three families, of which only the first family can build what we know as stable matter. Each family has 4 members, 2 quarks and 2 leptons. Thus divided, we see in the first family the up and down quarks, the neutrino, and the electron. All these particles have their own mass. The particles in the second and the third family are unstable and they decay. But they must have been important in the very early stages of our universe. There is so much more to tell about matter and antimatter, for instance. How can we perceive it? So much more that raises questions, too. Take the forces involved. We can now distinguish 4 different forces in nature. Some names are familiar: gravity, electromagnetism, and then weak force and strong force. All these forces are transmitted or carried by particles of force, a different kind of particle, each given its own name. There's the strong force, holding the quarks together, forming the proton, and forming the neutron. We say that this force is transmitted by the gluon. There's electromagnetism, playing a role in the existence of the atom. This force is transmitted by the photon. The 2 other fundamental forces are also linked with particles. Like the basic particles, force particles also have their own mass. There is a concept of an underlying symmetry. We call it supersymmetry. Atlas will search for evidence of this symmetry. Mass. Where does it come from? Some particles have a huge mass. At this point in time, we have theories proposing that mass is generated by a process known as the Higgs mechanism. If it exists, another particle has to be involved as well, the Higgs particle. It could be the ultimate creator of mass. One goal of the ATLAS experiment is to search for this particle and to reveal its properties. And why is a recurring word. Why only 12 basic particles? Why only 3 families? It's the why of our physics, as developed over centuries, coming to this point in time, point 2000 you could call it. "34 countries cooperate in ATLAS. The concentration point is CERN, Geneva. Here, the ATLAS detector will be integrated in the LHC, the accelerator that is the next step in our quest for answers. Beams of protons will collide with each other at an amazing energy of 14 TeV. Here we find superconducting magnets on a scale never before constructed. This huge accelerator, assembled in the same tunnel as its predecessor, is the new tool for a variety of experiments. And Atlas will be one of the detectors. The particle's journey is tracked, measured by different layers of the detector. 1. At the heart, the inner tracker. It measures the paths of electrically charged particles. 2. Wrapped around it, the calorimeter. It measures the energy of particles from the collision. 3. The muon spectrometer surrounds the calorimeter. Muons are like electrons but heavier, and these particles are not absorbed by the calorimeter. The momentum of these particles can be determined with high precision. There's one major design aspect as in the accelerator, the magnetic field. Extremely powerful and accurate as it has to be, the magnet, above all, requires space. Atlas measures 45 meters long and 22 meters high.
J'ai essayé de trouver, j'ai dit tiens, pourquoi pas trouver une solution où il n'y aurait pas ce problème de glisser, d'engasser quelque chose au risque d'abîmer.
Beyond dispute is the goal of accuracy. Strange, at places inside this huge machinery, the precision reaches 1/100th of a millimeter. A group of people. How could one group of people build a giant like Atlas? How could one country? Atlas is composed of many sub-detectors, of many parts that take time, take cooperation worldwide. You may wonder how scientists from all those countries communicate. Clarity is needed, agreement into fractions of millimeters, sometimes even further. So this will be the work in the years leading to 2005, the time it will take to create a fully operating Atlas.
On a 2 microns. Là, il faut le descendre.
Nee, dat is een hele mooie. Kan je die een beetje vergroten ook? Werkt het?
Deze?
Ja?
Ja.
Finally, there's the aspect we can hardly call an aspect, data technology. How far can we go in the design of computer systems? Atlas is going to have to handle extremely large amounts of data. Detected, converted, written to memory, communicated and analyzed all over the world. Physicists will gather their data and send it to their home institutes. The international family, different backgrounds, but the same scientific goal. Traveling with Atlas into the microcosmos, into an area of unknown physics. We do have some ideas of what to expect, but are alert for surprises.